Okay, let's talk about rotation a little bit more. Earlier in the previous video, we talked about similarity transformation. When we talk about similarity transformation, it means that if we want to find out the representation of a specific point in a specific frame, how are we going to deal with those kind of things? Because when it rotates about 30 degree, 90 degree, whatever, it is rotated absolutely. But when we are viewing this object, it is going to be a little bit different. So what we're trying to do in the previous slide is try to find out if if your object is rotating about specific axis for certain angles. When you change your point of view from one coordinate system to another coordinate system, what it is going to be look like, and how are we going to calculate the position based on the new coordinate system we want to observe. But that is one aspect of viewing those kind of system. The other thing is when we start to rotate, there are two types of rotation we're talking about. One is if we want to rotate about the current frame, how are we going to deal with the calculation? So the first case over here is we want to update the reference frame after each rotation. So if we think of point P in three different frames, then we rotate P from frame 0 to frame 1. Then it is straightforward. We just use this formula to come up with the the new coordinate after after the rotation. Keep in mind this is a given position, and this one over here is the position we want to derive. So we know this one is converted from frame 0 to frame 1. And if we know from frame 1 to frame 2, then this is another formula. If we replace, if we want to try to find the P from 0 to 2, what are we going to do is to do P0 equals to this transformation. But how are we going to find this transformation over here? The basic understanding is that we are viewing frame 1 from frame 2, from frame 0. Then we view frame 2 from frame 1. If we can cascade the calculation, which means we are in series of everything, then put the position in the back. That is how we describe the point converting from frame 0 to frame 2. Okay, so the transformation matrix is actually just like this. We just put everything in series, then we can find out the transformation matrix. But keep in mind, this is rotating about current frame. So let's look at this one over here. So if we are finding a rotation matrix that represents the rotation angles phi about the current y-axis, then followed by a rotation theta about the new z-axis. So when we are dealing with this one, we are having r, y, phi. That is going to give us the rotation cosine phi. The second column is going to be like this, and this is going to be negative sine phi. And this one over here is going to be sine phi, 0, and cosine phi. Now, if we want to rotate about the z-axis, then r z theta is going to be cosine theta sine theta negative sine theta cosine theta 0 0 1 0 0 over here. And after transformation, the coordinate is going to be look like from this shape convert into this specific shape. So if we are rotating about current frame, what is the transformation matrix is going to look like? So we know from the previous slide, we know This is about y-axis. This is about z-axis. When we try to do something like that from the original orientation to the destinated orientation, then we just multiply those two metrics together, and this is going to be our transformation matrix. If we are rotation about the current frame, that is pretty straightforward. Now, instead of rotating about current frame, sometimes we might need to say, okay, I have a satellite over here, and this robot is actually somewhere over here. So we want to find out what is rotation about this x, y, and z, which is fixed based on this one over here. What are we going to do? So R1 to 0, R1 0, R2 1, and R2 0 are rotations from the frame to frame as we did before. And R is rotation from 1 to 2, but specific in frame 0. So if we have those kind of things specified, what are we going to do is that we know the rotation if we are rotating about the current frame is like this. So from similarity transformation, we would like to, since everything is fixed to a specific coordinate, so what we need to do is everything convert back to its original position, just like what we did in the similarity transformation. So when we are dealing with that, after transformation from one, instead of using this part over here, we would need to have everything into something like this. So we know that this is going to be rotated about a fixed frame. So in other words, for rotation about a fixed frame, it is pre-multiplied by the second rotation. Now, we are talking about a lot of rotations so far. Let's talk about the parameters of rotations. So there are a few things you might need to take a look because those terms are used in many textbooks. One is Euler angle. The other one is the definition of roll, pitch, and yaw. And those are specific terms you might need to remember. Let's talk about Euler angles. So let's say, okay, we are rotating about z, y, z rotation. So if we are dealing with z rotation, it is something like this. And we are rotating about angle phi. And this is another angle we deal with when we are dealing with, when we are rotating about z-axis again. But between those two z rotation, we have another rotation in between which is rotated about y direction. So when we have individual transformation corresponding to a specific angle about the axes, so those are the transformation matrices that we want to do. So after a long calculation, this is going to be our rotation transformation matrix. So in other words, we are dealing with something like this. We are starting from x naught, sorry, this is y naught, x naught, and 0 naught. And we are rotating about z axis. So what we have is xa, ya, and this is going to be our za. And this time, we are rotating from xa, ya, and za. We are rotating about y-axis, so it's going to be this one with theta. So we're going to have, let's say this is zb and this is yb. And after the rotation, this one becomes xb. So what we are going to have is going to be something like this. before transformation. This is my ZB, YB, and XB. So we are going to rotate about Z-axis with another angle. So eventually, Y1 and Z1, X1, and this is going to be Z1. So let's change another color. So based on the transformation over here, the orientation of my new system is going to be X1, Y1, and Z1. If you want to find out the calculation of all the coefficients or coordinates or position, this is the matrix that you're going to adopt. Pretty straightforward, and this is something we're going to use when we are defining Euler angle, phi, theta, and the other angle is something we define as our Euler angles. Phi, theta, and this one are defined as Euler angle. Okay. Now, okay. So we learned the definition of Euler angles. Now we're going to talk about another definition, which is roll, pitch, and yaw angles. So when we design a robot, there are rotation around three axes, X, Y, and Z. But sometimes it might be a little bit difficult to communicate with people in this area. So in many cases, we would prefer to use some kind of terms to representing X, Y, and Z. So let's say you design a robot in the end of semester for your final project. And we will need to attach a three-dimensional space to this specific robot. And of course, they are corresponding to X, Y, and Z. Okay? Now, based on what we know earlier, the definition of the symbol over here is going to be psi. The angle over here is going to be phi. The angle over theta. The angle over here is going to be phi. This angle over here is defined as this one is as pitch, and this one as roll. So if you say your robot is rotated with some certain yaw angles, it means that it's going to be rotated in this direction. If you say it's rotated about some pitch angle, then it's going to be rotated in this direction. If it's going to be roll angles, it's going to be in this direction. So for instance, if you say your cat is rotated with 90-degree roll angles, then the orientation of the cat is going to be look like in this way. Right? So if you say your cat is rotated about 90-degree yaw angle, then your cat is going to look like this. So it should be like this. This is going to be y, this is going to be x, this is going to be z. But we have rotated to over pi. So this is how we use those kind of terms to define our rotation. Okay, so mathematically, how are we going to represent the calculation for the sequence that we're going to rotate the robot? So if you say I want to rotate it in a specific sequence, that is going to be yellow, peach, then roll it. So your cat is going to be rotated to this direction first. Then it will start to do peach. Peach is going to be in this direction. So I'll have my cat in a very weird orientation. Cat tail is over here. And it's going to be something like this. Okay, this is a head. Then after that, we start to do the rotation. So it's going to be in the climb up direction. Something like this. So this is something we're going to have our cat to do that. You will be laid down, then rotated, then move up. So this is going to be the three directions that we're going to have. But what this really means is that we are starting from x, rotating about x-axis, then do y-axis, and do z-axis. Okay, so this is not really something too fancy. And if we try to find out the position, first we will need to define what is my initial position. So that is just something we learned already, which is we define a position which is x, y, z in three-dimensional space. If we start to do the rotation, the first thing we need to do is to transform using the matrix about x-axis, then do that about y-axis, then do about z-axis. So the sequence, instead of start from left-hand side to the right-hand side, the first matrix we're going to attach to the whole system is going to be this one, rotated about x-axis. So it's going to be 1, 0, 0, 0, 0. Based on the matrix we defined earlier, this is going to be cosine phi, cosine psi, negative sine psi, and this is sine psi, and this is cosine psi. And this one must multiply by the position that we have over here. So after the rotation about after you multiply this one with another vector over here, the portion over here becomes another vector. So the vector is going to be rotated again, but this time it's going to be another matrix about y direction. So it's going to look like this. We're going to have cosine theta, sine theta over here. This one over here is going to be negative sine theta, and this one over here is going to be cosine theta. Of course, this is going to be my peach. Now, after this one, then we start to do the row. The row is going to be rotated about z-axis. So the matrix attached to this one, again, when you have just this one with the vector over here, then it becomes another vector. After you have a vector multiplied by the transformation matrix, it becomes another vector. So this vector is going to be multiplied by another transformation matrix. This time it's going to be 0, 0, 1 in the third row. In the third column, it's also 0, 0, 1. The transformation over here is going to be cosine phi, negative sine phi, and this one is going to be sine phi, and this is going to be cosine phi. And this is going to be my transformation matrix. Or if you want to, this one is going to be R, Z with V dot R, Y with angle theta, and dot r x with psi. So this is a transformation matrix that we're going to use. If you explain everything, use MathCAD or whatever, MATLAB or anything like that, this is a 3 by 3 matrix. Sometimes it might be convenient for us if we know the sequence is going to be in this, in this specific order, then we can just use a big matrix to do all the calculation. But if you don't have the specific order, then you might need to figure out what is the sequence, correct sequence, then you attach that in the correct order. Keep in mind, though we say it's going to be first x, the second y, and last one is z, it actually in opposite direction when we are doing the operation. Oh, this one over here is going to be row. So when you are dealing with those kind of things, keep in mind how the order or how the sequence is going to look like. If you interchange the order of individual matrices, the result is not going to be the same. After you do all the calculation, you are going to have cosine phi, cosine theta over here. This is going to be sine phi, sine theta. This one is going to be negative sine theta. And the second one is going to be negative sine phi, sine, cosine psi, plus cosine phi, sine theta, sine psi. This one over here is going to be cosine phi, cosine psi, plus sine phi, sine theta, sine psi. And this is going to be cosine theta and sine psi. The last column over here is going to be sine phi, sine psi, plus cosine phi, sine theta, cosine psi. The second component in this column is going to be negative cosine phi, sine psi, plus sine phi, sine theta, cosine psi. Over here, this is going to be cosine theta, cosine phi, and this is going to be my matrix. I know this part might be blocked by another smaller video. You can always find this transformation matrix in your textbook. But if you can do a little bit practice using MATLAB or using MathCAD, this is actually pretty straightforward. You can also do everything manually, though it's going to be a little bit tedious, but this can be a very good practice to understand what's going on over here. So when you are doing row, pitch, and yaw angles, this is how we do in the transformation. And keep in mind, you need to follow a specific sequence before you can actually come up with the correct transformation matrix.